This video is on solid revolution. I have this yellow region right here, and then I'm going to revolve it about the line x equal to 5, and then I'm going to use the shell method to find the volume of the solid revolution. Here's the yellow region again. So the top of the region is bounded by the graph y equal to 0.5x squared plus 2. And then on the right side, this is the line x equal to 4. And then over here on the left, y-axis. And down here we get the x-axis. And so now I'm going to revolve this region, this yellow region, about the line x equal to 5. And when we do that, then this is what we'll get. So we get this solid revolution right here with the hole in the middle, and the hole is just a cylinder. We're going to use the shell method, and we're going to fill the solid revolution with shells, and they would look like this. And so here I'm dividing the solid revolution into 8 shells. Cylindrical shells. And so here is shell number 1. So notice that the radius, the inner radius, is from the axis of revolution, the line x equal to 5, to here. Right here, this is 0.5, and so the inner radius will be 4.5. And then the outer radius is from here to here, which is 5. And therefore the average radius, which is right in the middle, is 4.75. So for shell number 1, the average radius is 4.75. And then right here, this is 0, and this is 0.5. So right in the middle, right here, this is 0.25. And so to get the height for this shell number 1, we would use the value 0.25 and the equation y equal to 0.5x squared plus 2. In the place of x, we would have 0.25. And then that will give us a height of 2.03125. And the thickness for shell number 1 here is 0.5. The volume of a cylindrical shell is 2 pi times the average radius times the height times the thickness. So in this case, we get 30.311. And then here is shell number 2. The outer radius will be from the axis of revolution to right here. And then the inner radius will be from the axis of revolution to right here. And so the distance from here to here is 4.5, and then the inner radius is 4. And so the average radius will be 4.25. And then the right in the middle right here, this is 0.75. From here to here is 0.5, and then from here to here is 1. So right here is 0.75. And then to get the height, we would use the x value of 0.75. So in the place of x right here, put 0.75. And that will give us 2.28125. And thickness again is 0.5. And so the volume for this shell number 2 is 30.459. And then here's shell number 3. The distance for the outer radius is 4. The distance for the inner radius is 3.5. So the average radius for the shell number 3 is 3.75. And then at the middle right here, the distance from here to the y-axis is 1.25. So right here, this is 1.25. And then to get the height for this shell, in the place of x here, we would put 1.25. And then that will give us 2.78125. Thickness again is 0.5. So the volume for shell number 3 is 32.766. And then here's shell number 4. volume is 36.055. Cell number 5, volume is 39.147. Volume number 6 is 40.865. Volume number 7 is 40.031. And volume number 8 is 39.270. Now let's add the volumes of the 8 cells together. Then we'll get 288.90. And so if we divide the solid of revolution with the hole in the middle into 8 cells, then we get a volume of approximately 288.90. Instead of 8 cells, suppose we divide it into n cells. Then this is one of the cells. Let's call it the ith cell. And so let's find the volume of this ith cell. And so first, I'm going to divide the interval from 0 to 4, right here, 0 to 4, into n sub-intervals. So the first one here, let's call it x sub 0, which is 0, and then x sub 1, x sub 2, and then we'll get to the ith interval, and this is x sub I minus 1, x sub I, and when we get to 4, then we'll get x sub n. And so for this ith interval, that's where this ith shell or cylindrical shell comes from. And so right here, for this ith shell, then this would be x sub I minus 1, and this would be x sub I. If there are 4 shells, then the thickness of each shell will be 1. If there are 40 shells, if we divide the solid of revolution into 40 shells, then the thickness will be 0.1. And then so in general, the thickness of each shell will be 4 over n. Let's call the thickness of the ith shell over each cell, let's call it delta x. And now let's find the volume of this ith shell. So the ith shell, for the ith shell, it comes from this ith interval right here. So this right here, the value right here would be x sub I minus 1, and the value right here for the inner shell. So the inner cell, let's call it x sub I, meaning the distance from here to here is x sub I minus 1, and then the distance from here to here is x sub I. And then right in the middle, which is x sub I minus x sub I minus 1 dividing by 2, and let's denote that as x sub I star. So x sub I star would be the distance from the y-axis to right here. But notice that the distance from here to here is not the radius of this shell. The radius of this shell is the distance from the line x equal to 5, and then 2 here. And so the distance from here to here is 5, and then the distance from here to here is x sub I star, and therefore the radius of this shell will be 5 minus x sub I star. And then the height of this shell will be the distance from the x-axis up to the graph. And so right here, this is x sub I star, and therefore this point right here would be f of x sub I star. And so f of x sub I star will be the height of this shell. But f of x is 0.5 x squared plus 2, and so f of x sub I star will be 0.5 x sub I star squared plus 2. The volume of this ith shell is 2 pi times the average radius times the height times the thickness. The average radius is phi minus x sub I star. The height, which is f of x sub I star, is 0.5 x sub I star squared plus 2. And the thickness of this shell is, we call it delta x. And so this is the volume of this ith shell. And so once again, this is the volume of the ith shell. And now suppose we divide this solid of revolution into n shells. At the beginning of the video, I divided it into A shells. But now let's divide it into n shells. So this will be volume of shell number 1, volume of shell number 2, volume of shell of the nth shell. And then using summation notation, then we have I running from 1 to n with this expression right here. And so the volume of the solid of revolution with the hole in the middle will be approximately this sum right here. And then if we want the exact volume for the solid of revolution, then we need to divide the solid of revolution into an infinite number of shells. Allow n to run to infinity. And then we get this limit quantity right here. And then just like before, when this limit quantity, when it exists, then we defined it as the integral from 0 to 4. 0 to 4. And then this will be 2 pi, and then phi minus x, and then 0.5 x squared plus 2, and then dx. And then simplify this part right here, we get negative 0.5 x to the third plus 2.5 x squared minus 2x plus 10. And then the integral for this expression right here is negative x to the fourth over 8 plus 5x to the third over 6 minus x squared plus 10x. And then evaluating from 0 to 4, and then we'll end up with 272 pi over 3, which is approximately 284.83. And recorded at the beginning of the video when I divided the solid of revolution into A shells, then the volumes of the A shells was 288, and then here we got 284.83. The exact volume for the cylindrical, for the solid of revolution that we want using the shell method is 272 pi over 3. And then now let's also find this solid of revolution using the disk method, and then we'll see that we'll get the same answer. The process is going to be much more involved than the shell method. So now let's use the disk method to find the volume of the solid of revolution that we want, and we'll see that we'll get the same answer. For this solid of revolution with the hole in the middle, to find the volume of the solid of revolution, what we can do is this. Notice that the base right here, the distance from 0 up to 2, down here, this is just a cylinder. And then we can find this outer cylinder and then subtract it from the inner cylinder. And then for the part from 2 to 10 here, this looks like a bell. And so we can find the volume of this bell right here, and then subtract it from the bell, the hole or the cylinder in the middle. And so let's find the volume of this bell right here. And so if we're using the disk method, then we would slice this bell into many disks or many slices. And so this is one of the slices. So let's call it the ith slice or the ith disk. The axis of revolution is the y-axis, and therefore we need to solve this equation right here for x in terms of y. So we have y equal to 0.5x squared plus 2. Subtract 2 from both sides, and then we get y minus 2 equal to 0.5x squared. Multiply everything by 2, we get x squared equal to 2y minus 4. And then take the square root of both sides, we get x to be the square root of 2y minus 4. And then let's rewrite this equation right here. Let's rewrite it as the function g of y equal to the square root of 2y minus 4. And so this function here, the graph, is this part. So this is g of y equal to the square root of 2y minus 4. And then the interval from 2 to 10 here, since the bell right here, it ranges from 2 to 10. And so let's divide it into n sub-intervals. And so here we get y sub 0, which is 2, and then y sub 1, and then y sub 2, and we get to the ith sub-interval, and then 10 would be y sub n. And so for this disk right here, it comes from this ith sub-interval. The distance from the x-axis to the bottom of the disk will be y sub I minus 1. The distance from the x-axis to the top of the disk will be y sub I. So right here, this is y sub I, which is the distance from the x-axis to the top of the ith disk. The distance from here, from the y-axis to the graph, will be g of y sub I. Since the function for this graph is the function g of y equal to the square root of 2y minus 4. Now, the distance from here to here, that's not the radius of this disk. The radius of the disk is from the line, from the axis of revolution, the line x equal to 5, to the graph. And so from here to here is 5. From here to here is g of y sub I. And therefore the radius of this ith disk will be 5 minus g of y sub I. And so we get 5 minus the square root of 2y sub I minus 4, since the function g of y is the square root of 2y minus 4. And the volume of this ith disk will be pi times the square of the radius, which is this. So it'll be 5 minus 2y sub I, 5 minus the square root of 2y sub I minus 4 squared. And then the thickness of the disk, we call it delta y. So again, the thickness of the disk would be just for the ith sub-interval, it would be just y sub I minus 1. Let's denote it as delta y, since the thickness of all disks are the same. So let's call it delta y. And then simplify this part right here, we get 25 minus 10 times the square root of 2y sub I minus 4 plus 2y sub I minus 4. And then we get 21 minus 10 times square root of 2y sub I minus 4 plus 2y sub I. So this is the volume of the ith disk right here. Again, if we want exact volume for this bell right here, then we have to divide it into an infinite number of disks. And then just like before, it becomes the integral from 2 to 10. So 2 to 10, which is from here to here, 2 to 10. And then we get the integral pi times the expression 21 minus 10 times the square root of 2y minus 4 plus 2y. And then here we get dy. And then evaluate this definite integral right here. It will come out to be 152 pi over 3. So we have just found that the volume of this bell right here from 2 to 10 is 152 pi over 3. And then this cylinder right here at the bottom from 0 to 2, the radius of this cylinder is 5, the height is 2, so the volume will be 50 pi. And then the volume of the cylinder in the middle right here, the radius is 1, the height is 10. So the volume of the cylinder in the middle here is 10 pi. And so the volume of the solid of revolution here, the whole thing without the hole in the middle, will be the 50 pi for the bottom here cylinder, and then 152 pi over 3 for the bell, and then minus the cylinder in the middle, which is 10 pi. And we get 272 pi over 3, which is exactly the same thing that we got earlier when we used the shell method. And that's the end of the video.